derived physical quantities. Our next derived physical quantity is force. Its symbol is the capital F. So a force is a push or a pull, a product of mass and acceleration. So force equals mass times acceleration. This is Newton's second law of motion. Acceleration equals force divided by mass. So they're the same thing. The acceleration of an object is directly proportional to the net force applied to the object and inversely proportional to the object's mass. So the more force you put on an object, the greater the acceleration. The more mass an object has, the less the acceleration. Another correct way of saying Newton's second law of motion. The net force applied to an object is equal to the mass of the object multiplied by its acceleration. A force is required to accelerate an object because the object has mass, and the object has, therefore, inertia. Inertia of the object serves to oppose the change in motion. Remember Newton's first law. An object in motion wants to stay in motion. An object at rest wants to stay at rest. Therefore, a force must be applied to overcome inertia. A force can cause matter to be distorted. And remember, it's elasticity that enables the recovery from distortion, unless that force exceeded the elastic limit. A force can also cause matter to be accelerated. A force is therefore defined as a push or a pull, or something that imparts acceleration to a mass. Force is a vector quantity. We have to specify its magnitude and direction. It does matter whether the force is acting left, right, up, or down. Imagine one of those kitchen doors that swing open. If someone's pushing a force inward and someone else is pushing a force outward, the door is not going anywhere. So the direction of the force matters. There is a pressure of 100,000 newtons per meter squared impinging on your eardrum. So why doesn't your ear cave in with this pressure? Because there's an equal amount of air pressure in your middle ear space that keeps your eardrum from popping in or popping out. When you go up on an airplane or when you change pressures very quickly, like an elevator to the Empire State Building, initially you're at sea level. So the air in your ear canal is at sea level, and the air in your middle ear is at sea level, and your eardrum is perfectly happy with these two pressures pushing on it and balancing it out. When you go up in the sky, all of a sudden you're way above sea level, and the air in your ear canal is much thinner than the air that's still in your middle ear space. And that's why your ears feel full, because your eardrum is being pushed outward by the denser pressure in your middle ear space. So what do? You chew gum, you swallow, you open your jaw, you try to open your eustachian tube to air out the middle ear space to balance out the pressures. We'll talk more about this in the anatomy and physiology part of the class. Force is measured in newtons. A newton is defined as a force that is required to accelerate a mass of 1 kilogram from a velocity of 0 meters per second to a velocity of 1 meter per second in 1 second. Pressure. Force per unit area. So pressure, lowercase p, is another derived physical quantity. Pressure equals the force over an area. So when we talk about sound, we're not particularly concerned with measuring the force exerted by one molecule on another. Instead, we want to determine the sum of many such small forces that act on some surface, the eardrum, for example. To do this, we're concerned with the amount of force per unit area, also known as the pressure, and pressure is measured in pascals. Pressure equals force over area, force per unit area, measured in pascals.